Okay, this is a lecture on notes part one. This is reaction rates and reversible reactions. And so we're going to go through this for you guys. Notes are posted on Google Classroom if you need them. And we'll get you guys going here and seeing how this works. So the first thing that we want to bring up when we're talking about reaction rates is the idea of collision theory, which states for a reaction to occur, you must have particles colliding with enough kinetic energy, that's movement energy, to break bonds or form bonds. Okay, so that's key thing number one, is that we've got to have that happening. Okay, there's a short video here that I want to show you guys, and let's just watch this.
Here's a beaker of cold water and a beaker of hot water. When you add sugar cubes to them, the one in the hot water will dissolve faster than the one in the cold water. To explain the different rates of reactions, Max Trotz and William Lewis came up with collision theory in the early 1900s. The first assumption of collision theory is that the particles must collide with one another in order to react. Most particles will act like billiard balls in a game of pool, and when they collide, they bounce off each other. The collision itself isn't all that's needed for a reaction to occur. The particles also need to have enough energy, enough speed, to break and form new bonds when they collide. The minimum energy required for a reaction to occur is called the activation energy. Some reactions require very little, and some need a lot more to get started. Generally speaking, most reactions will occur faster when the temperature is increased, because temperature is the average kinetic energy of the particles. With more kinetic energy, they will be more likely to have enough activation energy for the reaction to occur. But for some reactions, there is still one more factor: orientation. Even if the particles collide with sufficient speed, if they aren't at the correct angle, a reaction won't happen. In this example of nitrogen monoxide and ozone, the reaction didn't occur because the oxygen of each molecule touched during the collision. In this collision of the same two molecules, the nitrogen touches an oxygen and the reaction occurs, making oxygen and nitrogen dioxide. The orientation was correct, so the reaction could occur. So in summary, the three key ideas of collision theory are that particles must collide to react, they must have sufficient energy to break and make new bonds, and they must collide with the correct orientation. Thanks for watching this episode of Teacher's Pet. Don't forget to like.
Okay, so as you see in the video, they've got to have enough energy, like we see here. They've got to be pointed at each other at the correct angle, okay? And then they've got to hit with enough energy to break those bonds. So they need to collide, they need to be oriented at each other, and they need to connect. They need to hit with enough kinetic energy to break those bonds. So that's what collision theory is stating. Now, they mention activation energy, which we commonly call E sub A in chemistry. So the sub A is shown there. And that's the minimum energy that colliding particles must have in order to react. So if you look at this guy pushing the boulder is starting up higher and ending up lower, which should be an easy trip down a hill. But before it can get downhill, he's got to get to the top of this hill at that spot. Once he gets it there, it'll start rolling on its own and get going. And this picture is very similar to an energy diagram that we see when we're looking, at things in chemistry. So let's go here. Let me just get rid of this stuff. And we have the energy diagram shown here. There's an easier way to do this, but I'm going to do it the hard way because it's Markarian. And so we have, boy, I'm really going to take some time here erasing this. I think I got it all. Okay. So for activation energy, it's shown here on an energy diagram. Now, you guys have seen these before where we have reactants going to products, and this would be exothermic because it's going downhill. So the delta H on this thing would be negative. Okay. The activation energy is shown here, and that's the energy you've got to overcome to get that to happen. Now, This is like striking a match. I mentioned this in our Google meeting yesterday, but when you're trying to strike a match, if you don't strike it with enough friction energy, that thing's not going to light. Okay. So when you're striking a match and it doesn't light, it's like it's getting to there. It's like I don't have enough energy. So I'm just going to go back to being reactants again. Okay. Um, but if you do strike it with sufficient energy, it gets up to there and then it drops. Okay. And you start losing the energy. Now you lose the energy from the match head as heat and light. That's what you see with the flame, and it's exothermic. Um, Activation energy on an endothermic diagram would be the same idea. We'd start with reactants and then end up with products, but you still have the activation energy bump that's there. Okay, for that. So those are some things that you want to keep track of, as we're going through this stuff. Okay. All right. So let's look at the next slide. And okay, so we have a review of the heat of reaction, or delta H. We also call that the change in enthalpy or the change in heat. Different names, all the same thing. It's also known as Q, we've talked about, from Q equals MC delta T. When you're looking at this, just keep in mind, we mentioned this just a few seconds ago, delta H is negative. If that change is negative, it's exo. If the change is positive, it's endothermic. So the diagram can give away, which one it is. As always, we just added in the extra E sub A, the activation energy on the diagram. Okay. And so that's where we're at. So let's look at the next slide here. The activated complex, we mentioned this yesterday in the meeting, but if you weren't there, you have it here. We're going to show you what this looks like on the energy diagram on the next slide. There's a little video in the corner. I'm not going to play this one, but you guys can go to the notes and look at the video, and it really gives you a good picture of an activated complex for that. But it's a short-lived, like really quick, high energy molecule that forms just for fractions of a second. And it's where the reactants collide at that one spot. They're like one big molecule for just a split second. If they hit hard enough at that point, that's where they start breaking bonds and reforming bonds into products. We also call this the transition state. And again, the activated complex is right here. Okay, so where reactants meet up and collide with enough energy is right there. If they can get past that point, they start forming products. Okay, if they don't, then they will not form products. They go back. So they got to get to the activated complex to react. Okay, so that's a rule. Okay, so reaction rates. There are many things that can speed up or slow down chemical reactions, and they're listed here, and we're going to go through each of them. But temperature is a big one. Okay, temperature is defined as average kinetic energy of particles. Okay, so if we increase the temperature, we're going to increase the kinetic energy. Okay, if you increase the kinetic energy, you get more collisions. And that's what this all comes down to. How do we get more collisions so we can get a faster reaction rate? Okay, some of the other ones that are shown here, we have concentration, particle size, we'll get into that, and the use of a catalyst. Okay, so for temperature, higher temperature equals faster reaction rate, as we just said, and it makes sense. You get more collisions per second at higher temperatures. If we have a lower temperature, you get a slower reaction rate because you're decreasing the number of collisions per second. Okay. Good example of lowering the temperature to slow down reactions is putting your food in a refrigerator because it slows down the spoilage of food. I mentioned this in the meeting yesterday, but the minute they pick vegetables in a field, or we harvest grapes here at the ranch, the minute those grapes come off the vine, they are cut off from their life source of the vine and they slowly start to decompose and spoil. Okay. So putting food in the refrigerator is basically slowing that down so that it'll stay longer, it'll keep longer. Okay. You put it in a freezer, it does it even better. But that brings other problems like freezer burn and things like that over long periods of time. But It's really a fight against the clock with food, whether it's, meat, vegetables, fruit, whatever. It's really a fight against the clock, and you're trying to slow it down. Okay, temperature can do that. Consequently, you want to cook something, you got to heat it up. You got to get faster reaction rates going. An egg will never cook just sitting there on the counter because you don't have enough collisions per second to get the chemical reactions needed to cook that egg. Concentration. Now, concentration, just think about how much stuff in a certain volume. Okay. And when I think concentration, I think juice. When our kids were little, and when you guys were probably little, you don't give kids full concentrated juice. You give them juice that's been watered down, diluted with water. And so, like, we used to do 50%. So 50% water, 50% juice. And that would lower the concentration because the acid isn't good for little kids, stomachs. So higher concentration of reactants, more reactants in a certain amount of space gives us a faster reaction. Lower concentration gives us a slower reaction. Okay. In chemistry, we use moles per liter as our concentration unit. We also use percent. Okay. Um, the name of that is molarity, and we use a capital M as the unit for that. And we'll often say, oh, this solution is 2 molar. Now let me explain what I mean by that. If somebody shows me this, I know that means 2 moles per 1 liter. That equals that, and we say it as 2 molar. Okay, so that's the naming convention we use, the nomenclature we use for that, in the unit. A good example of concentration and a reaction is if you take a piece of wood, a wood splint, a stick of wood, and light it at 21% oxygen, which is what we live in our atmosphere. It'll glow, but if you put it in 100% oxygen, the thing will just light up like crazy. And so that's a good example of that happening. And I'll post some videos of this for you guys on Classroom and on my YouTube channel so you can see them. But yeah, this is why we don't smoke at hospitals. There's a lot of oxygen tanks around there. There's whole rooms that are close to 100% oxygen that some people have to be in. And it's not that the oxygen's flammable, it's that the oxygen promotes combustion. It's part of the combustion reaction. And if you increase its concentration, that reaction speeds up, sometimes dangerously. Okay, so here's an example. We have 2 containers. They're cylinders with a piston that can go up and down. And so when you look at A, the piston is here, and let's say that this is 1 liter. Okay. And in diagram B, the piston's been pushed down so that it's at 0.5 liters. And let's say that each of these particles represents 1 mole. Okay. So in container A, we have 4 moles per liter, which I would write as 4 molar. Okay. In container B, we still have 4 moles, but it's per 0.5 liters, which means we now have, if you take 4 and divide it by 0.5, you're going to get 8 molar. So even though they contain the same number of particles, B is more concentrated. And if it's more concentrated, it has more collisions per second. Okay. So by squeezing a gas in a cylinder with a piston, you can get its concentration up and you can get the reaction to go faster. Okay. And that'll be important as we go through some of the stuff in this unit. Okay. Particle size. Particle size. Oh, whoops, sorry. Particle size, the smaller the particles, the faster the reaction. The larger the particles, the slower the reaction. In the video that I put in the notes, watch that video. I would open up the notes, go to this video, and see what they're doing with this thing. Lycopodium powder is a non-toxic, it's basically a spore from a plant that's highly flammable when it's in really small dust particles. Flour, you get the same effect. If you buy flour at the store to bake with, it can get potentially dangerous. If you have a room full of flour particles that are suspended in the air and you light a match, that room's going to go up in flames and possibly an explosion. So that's because the particles are so small. So when you're trying to, if you're trying to light a wood log, a log, this is my log here that we're looking at. If I try to light that, it's really hard to do with a match. Okay. But if I take and add kindling underneath the log and light that, then I can get it to go. The kindling is still wood, but it's in smaller particles. Okay. And that it should make sense to us that smaller particles are easier to get, you know, reacted. Um, Catalysts will speed up a reaction without being used up in the reaction. So there are certain chemicals you can add to certain reactions that will speed them up. And I'm going to post videos of this as well for you guys so you can see it. One of them is the genie in the bottle. Another is elephant toothpaste. But you guys will have some links to those so you can see them. A biological catalyst is known as an enzyme, so which you guys have heard about in biology before. And enzymes speed up reactions in your body. Like, for instance, in your stomach, there's enzymes that at a certain acidity level will kick in and cause you to digest food faster. Without those enzymes, it would take you way longer to digest the food. So those are some things that can speed up reactions. There's another video here that's really good. It's a couple minutes long. It's animated, which I always love. But watch that as you guys have time. Now, the effective catalysts. When you're using a catalyst in a reaction, what it does is lower the activation energy, E sub A. And you notice that it took what was once the activation energy like that and lowered it there. And that effectively makes the reaction easier to get started and makes it go faster. So by lowering the pathway here that you can see starting with the reactants, we lower it, it's going to make the reaction go faster. Okay. So you should be able to draw that on a diagram, or interpret it as, if we have path A versus path B, which one is catalyzed, which one has a catalyst involved, it's going to be A because it's lower. Okay. And that's all that means. Catalytic converters are in cars and they speed up the conversion of harmful gases from the engine at this spot to less harmful gases that hit the exhaust. So all new cars have catalytic converters in them. They've been putting these in cars since the 70s when air pollution was really bad coming out of cars. It was, you'd see black smoke. So they put those catalytic converters in there to fix that. And so it's a good real world example of using a catalyst to help us. And it speeds up the conversion of harmful carbon monoxide, NO2, NO3. Those help contribute to smog. And we end up with more carbon dioxide, water, and nitrogen. The carbon dioxide obviously is an issue, but it's less toxic than the others. Okay. And the catalyst they put in this stuff is platinum, which is why catalytic converters are so expensive. Like just a normal catalytic converter is anywhere from $200 to $600, okay, to replace. Inhibitors are substances that are kind of anti-catalysts. They will stop catalysts from working, and they work by reacting with the catalyst itself, which poisons it. Some examples of those would be some of the things that are in food, like antioxidants, such as vitamin C or E. Those are always good to take. And the kinds of foods that have antioxidants in them are usually the things that don't taste as good. But broccoli, carrots, corn, squash, tomatoes, green tea, coffee, etc. Some of those taste good to me, obviously, but they're vegetables and fruits and things that can help us. So that's the inhibitor itself. Okay. So we're going to stop with this part of the notes. I'm going to have a second video that goes into the reversible reactions part. So stay tuned for that one. It'll be coming soon. Okay.